To begin the examples of chapter 2, the first thing we're going to do is we are going to formally derive the equations that describe 1D motion under the definitions that we have for acceleration and velocity. Now, when something is a definition, that is basically saying that everyone has gotten together and we all agree that this new thing we call acceleration is described in this way. And this new thing that is velocity is described in this way. There is no underlying fundamental principle that we get acceleration and velocity from. They are more derived from. We just agree that this is what we call velocity, this is what we call acceleration. So to begin, I'm going to begin with the definition of acceleration. And the next thing I'm going to do is I'm just going to change some terminology. So here I wrote acceleration is defined as v final minus v initial over t final minus t initial. I'm going to redefine v final. I will just call v initial. I will just call v naught. That's v with a subscript 0. I will also redefine t final as just t and t initial to be 0. So you could pretend we begin timing with a stopwatch at t equals 0. Then we click to end timing with our stopwatch at some time later that I just call t. All I'm going to do is I'm going to take these redefinitions and insert them. I'm not going to actually do anything yet to this definition. So I could write acceleration is defined to be v final minus v initial over t final minus 0. Now I said before that if you see the definition symbol, the 3-line equal sign, you could, for all intents and purposes in this course, just think of it as an equal sign. So I'm going to write it like that. T minus 0, that's just going to be equal to t. So I could then write A is equal to v minus v initial over t. Now, if I do something to one side of an equal sign, I have to do the same thing to the other. So I'm going to multiply both sides of this equation by time. So multiply that by t. And when I do that, the t's will cancel upstairs and downstairs on the right-hand side. T times a, I'm going to write that as at. I'm just rearranging the order of multiplication. I'm not doing anything in the next line, so I have a times t. And here I have v minus v initial. So this will be v minus v initial. And at this point, I could add v initial to both sides. So plus v initial plus v initial. And when I do that, on the left-hand side, I get v initial plus at is equal to v final. And at this point, I have derived one of the two equations that describe motion in 1D. For deriving the other equation that describes motion in 1D, I'm going to add two more redefinitions. I'm going to add x final. I will just call x for position, and initial position, x initial, I am just going to redefine as x naught. So again, this little 0 subscript here and here means initial quantity. If I do not have the subscript in these equations, that means final quantity. I'm not really doing anything when I make these redefinitions. I started by writing initial and final in my PowerPoint slides because I want to be very explicit which term means initial, which term means final. But before too long, you're going to be reading the textbook, working through problems, and this is the notation the textbook uses throughout, and I do want to also be able to match up with the textbook. So that is why I am changing this now. So we got one of our two important equations for this chapter. How do we get the second important equation? So what I'm going to do is I'm going to point out two things that we have. Number one, we have the definition of average velocity that we presented in the PowerPoint slides. So I could say V average could be written as V initial plus V final over 2. And this is average velocity. And if I just insert the notation I'm using here, I have V average could be written as V naught plus V over 2. But at the same time, I also could go with the definition of average velocity that we had given in the PowerPoint slides, where we also said V average could be defined as delta x over delta t. So I also could write V average as V average is equal to x final minus x initial over t minus 0, which I'm not going to bother writing. So if I want, I could say, look, here I have V average is x minus x initial over t. Here I have V average is V final plus V initial over 2. So, well, here's a V average, here's a V average. They're going to be the same thing, so let's just combine them. So I could write V initial plus V over 2 is equal to x minus x initial over t. Now what I'm going to do is I am going to just mess with some algebra and see where that leads. So let's bring t to the other side. If I multiply both sides of this equation by time, again, I have the same thing downstairs and upstairs, so they cancel. On the right-hand side of this equation, I will get x final minus x initial. On the left-hand side of this equation, I will have, I'm going to call this 1/2 times t times v initial plus v final. I'm going to just write it like this. I'll just make this neater. And what I'm going to do at this point is I will then replace v here with this term here. So what I'm going to write next is 1/2 times t. Then I have v initial plus v final, but v final is really equal to all this stuff here. So v final is really v initial plus at. I am being careful with my parentheses to make sure I am consistent. And then I have x minus x initial. So here's equals x minus x initial. Now at this point, I am just going to go through some algebra and see where that leads. So, okay, 1/2 t v plus v naught plus at. I have a whole lot of plus signs, so I could get rid of this parentheses inside here. So the next line would look like 1/2 times t v naught plus v naught plus at equals x minus x naught. Now in the next line, I am going to write, okay, I'll do everything in the parentheses first, so I could write this as 1/2 t. Then this will be v naught plus v naught gives me 2 v naught plus at equals x minus x naught. Now what I am going to do is I have a 1/2 t. I'm going to factor it in. So 1/2 t will be multiplied in here and in there. So 1/2 times t times 2v naught. So I have 1/2 t times 2v naught plus 1/2 t times at equals x minus x initial. And at this point, I'm going to address each term individually. 1/2 times 2, that just gives me 1. So this term will end up being t times v naught. I'm going to just rearrange the order and write it as v naught times t. So that is this term here. 1/2 times t times a times t, that will be 1/2 times a times t squared. And then I have equal to x minus x initial. And I'm going to erase this. And now if I add x naught to both sides, doesn't matter where I add it to, I will have x initial plus v initial t plus 1/2 at squared is equal to x final. So we have derived, using only some definitions of what we present, the two equations that describe motion when you assume constant acceleration. Now, as a practice, if you want, take a new piece of paper, work out scrap paper before putting in your notes. Using these two equations, combine them in a certain way to arrive at v squared is equal to v initial squared plus 2a x minus x initial. As I said before in the lecture slides, this equation is not new information. These two you could do everything in chapter 2 with these two equations only. However, sometimes that will be a little bit more work. If you prefer, sometimes this equation will save you some lines of math, and that isn't always the worst thing. So this equation does not give you any new information, but it can make your life a little bit simpler. So combine these two equations in a certain way to arrive at this line here. The last thing I want to say before I conclude this first example video is, let's rewrite these two equations and look at what they are telling us. So here is one of the important equations. We have x final is equal to x initial v naught t 1/2 at squared, and we have v final is equal to v initial plus at, and that's a square. So we are asking the question now, what would it look like if we were to plot these equations that we have? What would a plot of x as a function of time look like? When I write x as a function of time, that means I plot t on my horizontal axis and position on my vertical axis. If I were to plot velocity as a function of time, that'd be like saying I want velocity on my vertical axis and time on my horizontal axis. To begin, I'm going to look at this equation right here. So if I were to plot v equals at plus v naught. Now, I rearranged the order of addition. Mathematically, I did not change anything. But the reason I explicitly rearranged the order of addition is I could look at this and I could notice I have t on my horizontal axis, I have v on my vertical axis. This looks very similar to something you have seen in math courses, where y equals mx plus b. In math, what we do is we say, okay, we could say the vertical is the y-axis, the horizontal is the x-axis, we make our plot. But when we're doing only math, we're not actually ascribing any reality to what is x and what is y. In physics, the math might be identical, but in addition to doing the math, we also are ascribing some reality. T and V here represent some real physical quantity that exists in the universe. Here, x and y are just ideas from mathematics. But if I look, the arrangement of all the terms here are the same as the arrangement of all the terms up here. When I do math, it doesn't matter what I call my symbols. I could call this x and y, I could call it a and b. It doesn't change anything with regard to doing a calculation. So I recognize that my horizontal axis aligns up with t, my vertical axis lines up with v, and from there I could say, well, the slope lines up with acceleration. So the exact same math that describes a straight line describes velocity under constant acceleration. And the initial velocity lines up with the y-intercept. Now, you might ask, well, why do I say t aligns up with x and a lines up with m? What if I were to just flip the order of multiplication? Mathematically, there's no reason we're not allowed to do that. But remember, we're assuming acceleration is constant. T is a variable. So t is something that is not constant. We need many values of t. There's no such thing as a variable a in this equation. So this is the equation of a straight line. So I could say this is a straight line. If I were plotting velocity as a function of time, and a straight line will look something like this, where the slope is my acceleration and the intercept is my initial velocity. I could perform a similar analysis, similar line of thinking to this equation over here, where if I were to say, okay, what is this position as a function of time? I look at this, and after a while I recognize, well, here we have just a number. X initial is a number, whatever it's going to be. Here we have just a number times time. 1/2 a. This is also just a number because a is constant. So times t squared. So if this is kind of like y equals, I'll say capital AX squared plus bx plus c. This is the equation of a parabola. And my hesitation was, I was about to write lowercase a, but then I realized I have a here and I don't want to confuse them together. So capital AX squared plus capital BX plus capital C, whatever numbers capital A, B, and C are, it doesn't matter. This is still going to be the equation of a parabola. So I could say that x as a function of time is just going to be a parabola of some sort. Now, where is the parabola? Does it curve up or curve down? Well, that depends on the specific numbers then we have for 1/2 a, v naught, and x naught. The last thing I'm going to say before I end this video is we said the equations we derived, this guy and v equals v naught plus at, these assume constant acceleration. So you might ask, well, what about scenarios where acceleration is not constant? How would we address those questions? And pragmatically, the first thing I'm going to say is in this course, you will not see those scenarios, and I'll explain why in a moment. This course is designed to be an algebra-based physics course, and so you will not encounter calculus. What I'm about to do on the board now, you will not need to do in this course whatsoever. So, what if acceleration was not constant? So, how would we address that? So, let's go back to how we derived these equations in the first place. We said A was defined as delta V over delta T. In the limit where the interval of delta t and delta v become infinitesimally small, acceleration will become dv over dt, where this is the derivative of velocity with respect to time. We're doing calculus now. What if acceleration is not constant? So let's make acceleration a function of time. Let's say acceleration is equal to 2t squared. I'm just making up some acceleration. Clearly, acceleration is a function of time. So to solve this equation, I would bring dt to the other side. So I would have a dt times an a is equal to dv. And then I could plug in the acceleration that we are assuming. So I could say dt times 2t squared is equal to dv. And now I want to find velocity as a function of time. So what I would do is I would go from the initial to the final instant. Here I would say take the integral from t initial to t final, which in this case I'm saying 0 to t under the convention we used earlier. And in this case we're looking at time, so initial time to final time. On the right side of this equation we're looking at velocities, so I am looking at v initial to v final. And so I integrate both sides. 2 would come out front. T squared integral, that will be t cubed over 3. And then dv here would be just v itself, then v minus v naught. So if we assume a non-constant acceleration as given right up there, I could say v is equal to 2/3 t cubed plus v naught. And then I would similarly find the position as a function of time. So I would say that v is defined as dx dt. This is the infinitesimal limit when we say v is defined as delta x by delta t. We make this limit infinitesimally small, velocity becomes that. And so at this point I would do something similar. I could bring dt to the other side, so I get dt times v equals dx. I could plug in the velocity I found here, so I would get dt and 2/3 t cubed plus v naught equals dx. And then I could integrate again from initial to final moment. So here I am integrating from the initial to the final over position. Here I'm integrating from the initial to the final over time. So I would solve these. On the right-hand side, I would get an x minus x initial. And on the left-hand side, I would get a 2/3. Then I would get t to the 4th over 4 plus v naught times t. So I would then bring x naught over and I would get x final is equal to x initial plus v naught t plus, that would be 1/6 t to the 4th. So I want to really emphasize, you will not need to do anything like what I did on the board in this class. The reason I am bringing it up is this is just an algebra-based course. You do not need to do calculus in this course. But if you were wondering, we said the important equations from this chapter assume constant acceleration. What if we do not have constant acceleration? What if we have acceleration that depends on time? Then you would have to go through a method something like this. That's just for if you were curious. But you will not need to do anything like that. For this course, what you need to know from chapter 2, most importantly, among some definitions, don't forget to be consistent, all that good stuff, is A is constant, This will be the assumption we use, and we have x final is x initial plus v initial t plus 1/2 at squared, and v final is v initial plus at. As far as I am concerned, these are the only two equations you need for this entire chapter. If you want to make your life easier, then this equation could be useful, but it's not necessary. This just means you'll have a couple of fewer steps when you're actually solving a math problem. X final minus x initial.